Hello everyone. In this lecture we will be solving another application of the Symmedian line. Here's a view of this problem. So we are given that a triangle ABC, sorry for the color choice, and let X be the center of spiral similarity that will take B to A and A to C. Show that AX, where X is that center of spiral similarity, coincides with the Symmedian of triangle ABC. So let's start by simply constructing our triangle and its circumcircle, probably that I would definitely need actually. Let me do it. It's easier to solve to draw the circle first and then fit the triangle inside of it. So I'll just do that trick as usual. So what I have is I have my triangle, so something like that. Okay, so that's my triangle ABC, and I have my circumcircle around the triangle. So what I claim would be the best is that, so because it is somehow related to the Symmedian, let's assume it is related to, because AX will coincide with one of the Symmedians of our triangle, obviously it will be the Symmedian related to A. Therefore I need the tangents at B and C, obviously. So let me try to draw these. So, and one smart move would be to draw the perpendicular bisector. So I know those three lines will coincide. So good. So that's my tangency point here. Let me call it as D here. So what I would now next do is, let's try to understand the problem. So there is a center of spiral similarity which will take B to A and then A to C, right? So in a sense, you can think of a point inside this triangle. So let me draw it for now, and then I will go ahead and erase my drawing. So somehow we need to find a point, and such that the point B will be mapped to point A, and then the point A will be mapped to point C. So therefore we are looking for a point which will do this trick actually. So which will that point should create two triangles. So that point X should create two triangles which will be similar actually. So that dotted angle will be the same here, and then this angle which has a line on it, so those two angles would be equal. So how can I construct a point X which will do this trick? And notice that the claim is that AX will coincide with the Symmedian. So the best way to prove this problem is actually to just first start drawing the Symmedian and then see if there's a natural candidate for the point X, and then I can show that that candidate will do the trick. So let me go ahead and draw that Symmedian first. Symmedian line here, and obviously the Symmedian line is a special line. It is the reflection of the median across the angle bisector. So but that's my AD. The natural candidate, and you can kind of feel it, comes by drawing the actually the circumcircle of triangle BCD here. So let me go ahead and draw that circumcircle here. So for this circle we have a natural candidate. I claim that this point of intersection between the Symmedian and the circumcircle of triangle BCD, let's consider that point. So that point is the point X prime, and let's see if this is a good point. In fact, let me go ahead and mark that point above the thing. So that's my point X prime, and let's do some angle tracing here to see if we can find some nice properties of that angle. Obviously the angles that I'm interested in is, as I suggested earlier. Oops. Okay, so here you go. So let's see if I can prove that angle X prime BA is equal to angle X prime AC, and in a similar way X prime AB equals to X prime CA. Then I would be done, obviously, right? Let's start with AB X prime. Okay, so let's do it. So angle ABX prime. So this angle over here, I claim is, so notice its relationship to that angle. So it's just that angle, which is BX prime D minus BAX prime, right? BAX prime. Obviously, those two angles, two internal angles would add up to an external angle here. So, and then I just realized that angle BX prime D, BX prime D is simply equal to angle BCD. Why is that? Because BX prime D subtends this arc BD on the green triangle, on the green circle, and that angle is also subtended, that arc is also subtended by this angle here. So therefore BX prime D can be replaced with BCD. And in a similar way, angle BAX prime can be replaced by angle BA. Well, this one is, for now, let's just leave it, but let's rewrite it as BAD here. And now BCD minus BAD is the same as, so BCD, angle BCD, I claim, is equal to angle BAC. Why would that be? In fact, that's because if you look at the tangency here, CD is a tangency line, so therefore BCD, when you compare it with our first initial circumcircle, will subtend this arc BC down here, but that arc is also subtended by this whole angle BAC as well, so I can replace BCD with BAC minus BAD. Now it's obvious that BAC minus BAD is simply this angle here, so which is angle X prime AC. So that's a very nice result. But then in a similar way, one can easily show that this angle is actually congruent to this angle here. So therefore angle ACX prime is congruent to angle X prime AB. But then we are done. So what I did show that the spiral similarity that carries B to A and A to C can be constructed by using these two similar triangles. Sure enough, those two similar triangles create the construction for mapping B to A and then A to C as well. So therefore, we just showed that X prime is the center of that spiral similarity. So, and as a result, X prime coincides with the point X given in the problem, and therefore AX, so that X prime here is simply the point X, therefore AX is on, it coincides with AD, or you can say that A, X, and D are collinear actually. So that solves our problem, collinear. So that solves our problem. Hope to see you in our next video.